Hi, I'm Hannah Ziegler, and my design project was on increasing the stiffness of a sheet of steel. So in this case, the material was already selected as steel, so the way that we would increase the stiffness is by changing the section profile. So in this case, we were looking to corrugate the sheet, and that would allow for lighter structures in stiffness limited design, as well as larger in-plane compressive loads without the sheet buckling. And we would also increase the natural frequency of the sheet so we could subject it to higher frequencies without failure. So the constraints for this project were we would need to keep the thickness within 5 of the thickness of a flat sheet, and we are looking to maximize the bending stiffness while also keeping it cost effective to manufacture. And we can do this by changing the section profile. So we're looking at 2 factors in this case, specifically stiffness and strength. We're going to focus on the one for stiffness because that's the objective we're looking to maximize. And that shape factor for stiffness is based on the second moment of area for the original design of the flat sheet, which is just based on the thickness, and then it's compared to the corrugated sheet design. Most often that's a sinusoidal profile, so it's based on the thickness of the sheet as well as the amplitude of that curve. And so if you look at the stiffness shape factor, you can see that we would be able to maximize it by choosing the largest amplitude of that curve while also remaining within our thickness limits, and that would allow us to maximize the second moment of area and maximize the shape factor. But if you consider that common sinusoidal profile, you only get stiffening in the direction that's perpendicular to that curve, so we eventually went with a hexagonal dimpled profile. One of the problems with this design, though, is you don't get equal stiffening in all directions. So if you look along plane A, you would get a larger compressive strength because those peaks are closer together. But if you look through plane B, it's a lower strength because those peaks are further apart. Additionally, with this design, the dimples would change the failure mode, so you need to be aware how you're loading this sheet if you need to be concerned with local buckling or not. So in summary, we are looking to maximize the bending stiffness of a sheet of steel, and we could do this by adding hexagonal dimples to the sheet profile, which would allow us to increase the second moment of area and increase the shape factor based on stiffness. And in order to get the largest shape factor, we would want to look at the largest amplitude for that corrugated profile. Any questions? Hi, I'm Sarah, and my design project was on table legs, making them either thin or light. So for the design description, the function was to make tube-shaped table legs with constraints on the material. So this case study had a pre-selected material of glass fiber reinforced polymer, and then each table leg had to be able to hold 50 kilograms without buckling. The objectives were to minimize thickness of the table leg or to minimize its mass, in both cases to ultimately minimize the cost of the table leg. And we could do this by changing the radius or the wall thickness of the table leg. So the model description began with 2 relationships for the geometry of the table leg. The first was for the shape factor of a hollow circle, and the second was for the radius of the table leg, which was derived from the area equation of a hollow circle and the second moment of area equation. The last relationship was for Young's modulus times the second moment of area, which was derived using the buckling constraint with a load of 50 kilograms and a 1 meter long table leg. So these relationships and constraints allowed us to plot a 4-plot diagram and also to make a rectangular selection area, which, as you can see, shows us that the lightest leg is going to have a shape factor of 10, but it's going to make it really thick, so it's going to have a radius of about 20 millimeters, whereas the thinnest leg is going to have a radius of about 5 millimeters and a shape factor of 1. But because the radius is so small, the table leg is going to be solid, and it's going to be about 3 times heavier as the lightest one. So in summary, the design objectives were to minimize mass or to minimize thickness of the table leg. The material selected was GFRP with a shape factor of 10 for minimal mass and a shape factor of 1 for minimal thickness, each because they satisfied one of the given design objectives. And in conclusion, for this case study, really only one objective can be satisfied at a time. If you were to try to meet in the middle and satisfy both constraints, you wouldn't really truly minimize either of the objectives.
Most professors give a final, and all students learn the most just before final and walk away without ever interacting with the professor. So I've been toying with this approach of getting to interact with you when you have learned the most, that is at the end of the course. And so that was some of the thought behind trying to experiment with having this type of a format where I actually get to hear from you at the end of the course, as opposed to just having you walk away and then forget everything in the course altogether. Which you might anyway, but at least I got one day out of you. So thanks for putting up with this experiment. And I hope through this course, as you saw through this week, you came across a number of different scenarios. As a design engineer, you came across a way to implement things in the class and hear about those implementation of a much wider cross-section of material options for various applications beyond stainless steel, mild steel, and aluminum alloys. And so, I mean, that was one thing that I hope was a useful takeaway. Not only that there's a whole universe beyond all of that, but also that there's a pathway to find that, and that just does not depend upon anecdotal information or familiarity or someone just telling you what to do. Right? That you can walk your way through that, and you can push back at a customer, at the boss, at a team member, in terms of providing a valuable input as to where innovation might come along and where a better product might emerge from. And that is what I wish for all of you in your career, that you are able to speak your mind, but do so after careful analysis and with a different perspective. And as you refine these skills and integrate that with a lot of the other aspects that you learn through your journey at UFL, hopefully that will all make you great design engineers. So thanks again.